let us have the second part of our discussion, which is about heat. So if we are given again the glass of water and if we would like to measure its temperature, we have to place a thermometer in contact with our system. So as we all know, energy will transfer from our glass of water going to our thermometer until both of them have the same temperature or until they have reached thermal equilibrium. And that energy that transfers from one object to another because of a temperature difference is known as heat. Or heat is defined as the energy in transit moving from a body of higher temperature to one of lower temperature. So again, there will be an energy transfer only or there is heat if there is a temperature difference between our objects. So how can we determine the amount of energy that is transferred? So given the two illustrations here, one illustration on the left side has a higher temperature and the other illustration here has a lower temperature. So how can we determine the amount of heat that is added or that was removed to our system? So the amount of heat depends on the change in temperature that happens in our system. It also depends on the mass of the substance and to the kind of substance described using its specific heat capacity. Or our heat or Q is equal to mass times C, specific heat capacity, times the change in temperature, or Q is equal to mc delta T. So again, the amount of heat added will have a positive sign and the amount of heat that is removed in our system will have a negative sign. And to compute again for the amount of heat that is added or removed, we will use this general formula for heat, which is mc delta T. For the units of heat, we have the following. Calorie, abbreviated as CAL or cal. Kilocalorie, also known as calorie with a capital C, with its abbreviation for kilocalorie as kcal, and for a calorie with capital C is abbreviated as capital C. British Thermal Unit, abbreviated as BTU, and of course the very famous unit which is joules or with a symbol of J. So again, these are the units of heat that we will be using. Let us consider this scenario. You put out an aluminum pan with food on it from the microwave oven. And you can barely touch the aluminum pan itself, but you'll get hurt or you'll burn your fingers if you try to touch the food it contains. So this scenario explains or is an example that different substances has different capacity to absorb heat. And that is explained using the concept of specific heat capacity. So to define specific heat capacity, it is the quantity of heat required to change the temperature of a mass of substance by 1 degree. Our symbol for specific heat capacity is small letter C, and the units are joule per gram times Celsius degree, joule per kilogram times Celsius degree, joule per kilogram times Kelvin, calorie per gram times Celsius degree, and it can be British Thermal Unit or BTU per pound times Fahrenheit degree. So to explain more what is specific heat capacity, let's have the example. So water has a specific heat capacity of 4.186 joule per gram times Celsius degree. So it means that we need 4.186 joule of energy so that a 1 gram mass of water will change its temperature by 1 Celsius degree. So again, when we say specific heat capacity, that is the amount of energy needed by a mass of substance to change its temperature by 1 degree. Let's have another example. Specific heat capacity of ice is equal to 0.50 calorie per gram times Celsius degree. So this means that 1 gram of ice needs 1 calorie of energy so that it will change its temperature by 1 Celsius degree. So here are the approximate specific heat values of some substances, and these are expressed in different units. Let us check our understanding about specific heat capacity. So based on the illustration, which has a higher specific heat capacity, water or sand, and explain. So based on the illustration, we can see that during daytime, the sand warms faster than water, which is 25 degrees Celsius already, and the sun is only 20 degrees Celsius. Therefore, we can say that our water has greater heat capacity than sand, meaning water needs more heat for it to increase its temperature. So, our answer is water has higher specific heat capacity than sand. And during nighttime, water is slower to cool because it absorbs more heat during daytime because it has higher specific heat capacity. Let us have our first example problem about heat. You are designing an electronic circuit element with 30 grams of silicon. The electric current through it adds energy of 8.0 times 10 raised to negative 2 joule per second. If your circuit element doesn't allow heat transfer out of the circuit, what is the final temperature of your circuit if it has an initial temperature of 10 degrees Celsius? So to analyze our problem, we have to identify the given. So we are given the substance, which is silicon, and its mass is 30 grams. Our circuit absorbs energy, which is 8.0 times 10 raised to negative 2 joule. So this amount of energy is the heat absorbed by our substance. We're also given the initial temperature of our circuit, which is 10 degrees Celsius. And since we are dealing with a silicon substance, we will be using specific heat capacity of silicon as 705 joule per kilogram times Celsius degree. And we are asked for the final temperature of our circuit, or T sub F. So to start with, our formula is Q is equal to mc delta T, or heat is equal to mass times specific heat capacity times change in temperature. Since we are looking for the final temperature, we have to know first what is the change in temperature that our circuit undergoes. So, dividing this equation by mass times specific heat capacity, or M times C, we can get the formula for delta T, which is change in temperature is equal to heat divided by mass times specific heat capacity. And we can now have the substitution, which is delta T is equal to 8 times 10 raised to negative 2 joule for our Q divided by 0.030 kilogram times 705 joule per kilogram times Celsius degree. Computing for this, we can have an answer for delta T as change in temperature is equal to 3.78 times 10 raised to negative 3 Celsius degree. Since we know the change in temperature that our circuit undergoes, we can now compute for the final temperature. And that is, the final temperature of our circuit is equal to the initial temperature plus the change in temperature it undergoes. Substituting our values, we have T sub I as 10 degrees Celsius, and the change in temperature we got earlier is 3.78 times 10 raised to negative 3 Celsius degree. Adding these two values, we will have our final answer as 10.00378 degrees Celsius. So this is the final temperature of our circuit after absorbing a certain amount of energy or heat. Example problem number 2. In an effort to stay awake for a review session in preparation to a major exam, a student makes a cup of coffee by heating a 0.4 kilogram of water using a 200 watts electric heater. How much heat must be added to water to raise its temperature from 25 degrees Celsius to 100 degrees Celsius? So let us analyze again our problem by identifying the given. So we are given mass of water, which is 0.400 kilogram, the initial temperature, which is 25 degrees Celsius, and the final temperature, which is 100 degrees Celsius. And since our substance is water, we will be using specific heat capacity of water, which is 4,186 joule per kilogram times Celsius degree. We are asked to look for the amount of heat or find Q. So to start with, our general formula again is Q is equal to mc delta T. And we can have this direct substitution. So for our Q, that is mass, which is 0.4 kilogram, times C, which is 4,186 joule per kilogram times Celsius degree, multiplied by the change in temperature, which is the final temperature minus initial temperature. So 100 degrees Celsius minus 25 degrees Celsius. Computing this, we will arrive with an answer of Q is equal to 125,580 joule, or if you want to express this in scientific notation, this is also equal to 1.26 times 10 raised to 5 joule. So this amount of energy is the needed energy by our water for it to change its temperature from 25 degrees Celsius to 100 degrees Celsius. Let us have some situation or example problems that involve two or more substances together. And for us to do that, we will be dealing with calorimetry, or the quantitative measure of heat transfer. So the amount of heat that is being absorbed by one substance and the amount of heat that is being released by another substance can be calculated experimentally using an apparatus or instrument called as calorimeter, which you will encounter this in our experiment. So for us to know the amount of heat that is transferred from one object to another, we have to identify the concepts how this happen. So if we are given two objects, such as objects A and B, and these two objects are in different temperature. So object A has higher temperature than object B. And if they are put in contact together, object A will transfer energy going to object B because heat transfer always occurs from hotter object to cooler object. So that is the directionality of heat transfer. That is from higher temperature going to lower temperature. And since they are in contact with each other, the transfer of heat will continue until both objects are at the same temperature or they attain thermal equilibrium. And if they are in thermal equilibrium with each other, the two objects has the same temperature and heat flow will stop. So the amount of heat that is lost by the hotter object, for this case object A, is also the amount of heat that is gained by the cooler object, which is B. So expressing that in an equation form, that is negative Q lost by the hotter object is equal to the Q gained by the cooler object. So we will apply these concepts in solving problems wherein we have objects that released or lost heat and we have object that gained or absorbed heat. Let us continue with our example problem. So this is item 3. To determine the specific heat capacity of an object, a student heats the object in 100 degrees Celsius boiling water. He then places the 38 grams object in a 155 grams aluminum calorimeter containing 103 grams of water. The aluminum and water are initially at a temperature of 20 degrees Celsius. If the equilibrium temperature is 22 degrees Celsius, what is the specific heat of the object? So let us analyze our problem by identifying the given. So from the first statement, we are given that an object was placed in a boiling water which has a temperature of 100 degrees Celsius. So therefore, after some time, our object will have or will reach its thermal equilibrium with the boiling water. So our object will also have the temperature which is 100 degrees Celsius. So the initial temperature of the object is 100 degrees Celsius. And this object was transferred to an aluminum calorimeter. And our aluminum calorimeter has water on it. So from the second statement, our given are the initial temperature of our water, which is 20 degrees Celsius. And since the water and the container are in contact with each other, we can also say that the initial temperature of the calorimeter or T sub I cal is equal to 20 degrees Celsius. And of course, after some time, our aluminum calorimeter or the container, the water, and the object itself will reach thermal equilibrium. So if they reach thermal equilibrium, as stated in our problem, the equilibrium temperature is 22 degrees Celsius. So therefore, the final temperature of our water is 22 degrees Celsius. The final temperature of our calorimeter is 22 degrees Celsius. And the final temperature of our object is also 22 degrees Celsius. So again, the final temperature of our three substances, which are water, the aluminum calorimeter, and our object, are all the same because they reach thermal equilibrium. So aside from this given, we are also given the masses of those three substances, which are the mass of the object is 38 grams, the mass of the calorimeter is 155 grams, and the mass of the water is 103 grams. And again, for the initial temperatures of our objects, which was identified earlier, T sub I of the object is 100 degrees Celsius. T sub I of the calorimeter and water are both 20 degrees Celsius. And we are also given the final temperature of those three substances as 22 degrees Celsius. Since our calorimeter is made of aluminum, the container is made of aluminum, we will be using specific heat capacity of aluminum, which is 0.910 joule per gram times Celsius degree. And we will also be using the specific heat capacity of water, which is 4.186 joule per gram times Celsius degree. So these are the given out of our problem. And we are asked to look for the specific heat capacity of our object, or C of the object. Since we are given three substances here, we will start with our formula as negative Q lost is equal to Q gained. So out of the three substances, we will identify which substance or what substance will lost heat and what substance or substances will gain heat by checking their initial temperature. So our object has an initial temperature of 100 degrees Celsius, and the calorimeter and water both has initial temperature of 20 degrees Celsius. As we learned earlier, heat transfer happens from warmer object going to a colder one. So therefore, the heat lost will be coming from the object, and the heat gained will be the heat gained by the calorimeter and the water. So our negative Q lost is the negative Q by our object, and the Q gained will be the sum of the heat gained by the calorimeter and water. Expanding this formula, we will have negative mc delta T, so this is the amount of heat lost by the object, is equal to mc delta T by the calorimeter, so this is the amount of heat gained by the calorimeter, plus mc delta T, or this is the amount of heat gained by water. Since we are looking for the specific heat capacity of the object, or C of the object, we can now divide both sides by negative mass times the change in temperature of the object. And cancelling the common factors, we will now have the working equation for the specific heat capacity of the object as mc delta T of the calorimeter plus mc delta T of the water divided by negative mass of the object times delta T of the object. Let's proceed with the substitution of our given. So C of the object is equal to 155 grams times 0.910 joule per gram times Celsius degree times the change in temperature is 22 degrees Celsius minus 20 degrees Celsius. So this first set of values are the heat gained by the calorimeter plus heat gained by the water is 103 grams times 4.186 joule per gram times Celsius degree times the change in temperature is 22 degrees Celsius minus 20 degrees Celsius divided by negative mass of the object, which is 38 grams, times the change in temperature of the object is the final temperature, which is 22 degrees Celsius, minus initial temperature, which is 100 degrees Celsius. And computing for our final answer for the specific heat capacity of the object, we will have an answer of 0.386 joule per gram times Celsius degree. So this is the specific heat capacity of the object. Example problem number 4. An 800-gram piece of aluminum at 90 degrees Celsius is immersed in calorimeter of mass 60 grams with 1000 grams of water at 20 degrees Celsius. Assuming no heat is lost to the surrounding ore container, what is the temperature of the metal and the water when they reach thermal equilibrium? So let us analyze our problem by identifying the given. So our object is aluminum with a mass of 800 grams, and that is initially at 90 degrees Celsius. So initial temperature of the object is 90 degrees Celsius, and since our object is made of aluminum, we will use specific heat capacity of aluminum, which is 0.910 joule per gram times Celsius degree. This object is immersed in our calorimeter, and the calorimeter has a mass of 60 grams. The calorimeter has water on it with a mass of 1000 grams. Both the calorimeter and water have the temperature of 20 degrees Celsius. So the initial temperature of the calorimeter and water are the same, and it is 20 degrees Celsius. Since our calorimeter is made up of aluminum, we will use C4 aluminum for our calorimeter, and also we will be using C of water, which is 4.196 joule per gram times Celsius degree. This problem is looking for the thermal equilibrium of our system. So we are looking for the final temperature of the system. So again, as you can see, we have here 3 objects or substances that have different temperature. So combining these 3 will result to energy transfer, and after some time, they will reach thermal equilibrium. And that temperature final, when they reach thermal equilibrium, is the one we are looking for. So our starting equation is negative Q lost equals Q gained. This is the starting equation because we have here 3 substances with different temperatures. So therefore, there will be a substance that will lose heat, and there will be substances that will gain heat. So let's identify which of these 3 will lose heat. Our object has an initial temperature of 90 degrees Celsius, and the calorimeter and water has an initial temperature of 20 degrees Celsius. Since our object has the higher temperature, or this is warmer compared to calorimeter and water, therefore, our object will lose heat. And the calorimeter and the water will gain heat. So replacing negative Q lost, it will be negative Q of the object equals, replacing Q gained, it will be the heat gained by the calorimeter plus the heat gained by the water. Expressing Q as mc delta T, it will become the negative Q of the object will be negative mc delta T of the object is equal to the Q of the calorimeter is mc delta T of the calorimeter plus Q of the water is mc delta T of the water. Since we are looking for the final temperature, we can replace delta T as T sub F minus T sub I. So again, delta T is the change in temperature. And when we say change in temperature, we're always computing that using the final temperature minus initial temperature. So all we have to do is to replace the delta T of the object, the delta T of the calorimeter, and the delta T of the water using T sub F minus T sub I. So it will become negative mass times C of the object multiplied by T sub F minus T sub I equals mass times specific heat capacity of the calorimeter multiplied by T sub F minus T sub I plus mass times specific heat capacity of our water multiplied by T sub F minus T sub I. We can now substitute our given data. So again, the left side of the equation refers to the heat lost by the object, and the right side of the equation is the heat gained by the calorimeter and the heat gained by the water. So let us substitute the data for our object. So that will become negative 800 grams times 0.910 joule per gram times Celsius degree times T sub F, which is unknown, minus T sub I is the initial temperature of the object, which is 90 degrees Celsius, equals, let's have the right side of our equation, 60 grams times 0.910 joule per gram times Celsius degree times final temperature, which is unknown, minus initial temperature of the calorimeter, which is 20 degrees Celsius, plus, so we will deal with the heat gained by the water, which is 1000 grams times 4.186 joule per gram times Celsius degree times T sub F, which is unknown, minus T sub I of the water is 20 degrees. Simplifying our solution, we have to multiply first 800 grams by 0.910 joule per gram times Celsius degree. And that will become 728 joule per Celsius degree. So the unit gram will be cancelled. And still, we have to multiply this by T sub F minus 90 degrees Celsius equals, let's have the right side of our equation. So we will simplify first 60 times 0.910, and it will become 54.6 joule per Celsius degree. This is still multiplied by TF minus 20 degrees Celsius. And the last set of our solution, that is 1000 grams times 4.186 joule per gram times Celsius degree, it will become 4,186 joule per Celsius degree times T sub F minus 20 degree Celsius. Still, we can simplify this. So we will multiply 728 to T sub F, and we will also multiply 728 to negative 90 degrees Celsius. So that is 728 joule per Celsius degree times T sub F, which is negative, and then plus, so negative 728 times negative 90 will result to positive 65,520 joule. The right side of our equation is 54.6 multiplied by T sub F, which is 54.6 joule per Celsius degree times T sub F, and also 54.6 multiplied by negative 20 is negative 1092 joule. Plus 4,186 multiplied by T sub F will become 4,186 joule per Celsius degree times T sub F, and 4,186 multiplied by negative 20 will result to negative 83,720 joule. We will combine all terms that are the same. So, we will transpose all terms with T sub F on the left side of our equation. And those are negative 728 joule per Celsius degree times T sub F minus, so this will become positive, negative, minus 54.6 joule per Celsius degree times T sub F minus 4,186 joule per Celsius degree times T sub F. All of the quantities without an unknown variable will be transposed to the right side of our equation. So that is negative 1092 joule minus 83,720 joule minus 65,520 joule. And simplify our solution. So let us combine negative 728 minus 54.6 minus 4,186. It will become negative 4,968.6. The unit is joule per Celsius degree, and this is still multiplied by T sub F. Simplifying the right side of our equation, which is negative 1,092 minus 83,720 minus 65,520 will result to negative 150,332 joule. And since we're looking for T sub F, we can divide both sides by negative 4,968.6 joule per Celsius degree. So therefore, we can now compute for our final answer. So our T sub F is equal to negative 150,332 joule divided by negative 4,968.6 joule per Celsius degree. Computing for this, we will arrive with our final answer as T sub F is equal to positive 30.26 degree Celsius. So again, this T sub F means the final temperature when the object, the calorimeter, and the water reach thermal equilibrium. You may now proceed in answering the assigned problem to your class.